to the final Straxferno. Congratulations, you almost made it. There's just a small piece to go. So today we're going to talk about the final circle of Straxferno. This is the deepest you can go. This is about the mailboxes, about the concurrency backend that is used in Strax to connect all of these plugins and all of these things together. So because Strax has such a network-like structure, if you look at the graph, you see many plugins that are connected to each other. We can't have it just as we had in PAX, that there's a kind of linear sequence of things that we go through. Because we want to have this as a stream processing where really one piece of data can be processed by various plugins, and everything can stream through at the same time. And there are various ways, various different points where you can start. You don't always start with the raw data. You could start sort of halfway in the chain, and then there might be like 4 or 5 things loading from each other and all going towards a single aim. So what I'd like to do today is to first give you a kind of a brief overview of just what this mailbox thing is and how it works during an operation of Strax. Then we can look briefly at the exception handling, which is also another rather intricate thing. And then, as usual, we'll take any questions that you have. As usual, just interrupt me whenever you have a question on what I'm saying. And then we'll be done. So I hope that this system won't be necessary very long. If you've been at I think the last telecom before last, the analysis telecom, you already saw a new system by Yossi based on the streams package. That's really a package which solves very similar challenges. So that system will be different, but in the end, the challenges that it will have to solve will be similar. So I hope that what you learned today won't be completely wasted, even if the mailbox system is eventually replaced, as I hope it will be, because there is quite a bit of custom code in there. Okay. Right. So what is a mailbox? A mailbox is a class containing messages and references to threads of senders and subscribers. And a sender or a subscriber here is any of the usual agents that we've been talking about. So that could be a plugin that is computing something and maybe sending its results here. It could be a loader, so something that's loading from disk, sending its results in. The subscribers could be either, again, a plugin, but now it's one of the arguments of iter, right? So if you look at the plugin, this is code we looked at before. The iter method here has this iters dictionary as an argument. So somehow it's getting a dictionary of iterators over dependencies. So what happens when you call next on one of these iterators? It doesn't happen immediately. We zoom in a little bit. Okay, so there's fetch chunk that we talked about earlier. And inside fetch chunk, there's actually a call to next on the iterators. So what happens when you call next is that you enter this mailbox code. So you saw maybe where plugins are set up. So here you are in the processor, the threaded mailbox processor, in the initialization method. So let me skip over the first bit. But here's where this iter method is actually called. So it is called here, and here's where this argument is being constructed. So this iters argument, you get a subscription to these mailboxes. So this subscribe method will return an iterator that this iter method is iterating over. So as soon as you call next on it, you jump to a bit of code that lives in the mailbox class, specifically if you're in the subscribe methods. Let's see. Right, so specifically the underscore read method. So you jump to this code as soon as you call next, and then inside this code is, for example, a place where you wait for a new input. So a mailbox is just a piece of code that different threads can jump into when they need to retrieve a bit of input or retrieve a bit of output. or put away a bit of output. So the mailbox is kind of associated with the thing that's sending into it, and the others just have sort of a subscription on them. So I'm showing it here as though there is one sender and multiple subscribers. This is sort of the general situation. The only thing that you can have is that this sender is actually a multiprocessing plugin. So this, for example, if you're on the DAQ and this is raw records, then instead of every call to compute executing, it will be sent to a pool of processes that can do work for you, and those will then eventually go back to the mailbox. So there can't really be multiple senders, but in a sense it can be, because there are multiple processes that are dumping stuff into this mailbox, but it's all eventually controlled by one plugin. But it could be that the messages arrive out of order, and that is something that the mailbox will have to deal with, and it's one of the things it does deal with. Right, so it obviously tracks here the messages. So a message is, of course, just a chunk. The mailbox has its own numbering, which it should be the same as the chunk numbering. The mailbox is a way older part of Strax than the chunk classes. So these things used to be NumPy arrays, and they've now been changed into chunks. Other things it tracks, so for these subscribers, what has each subscriber already read? So here we have one subscriber that's read message 1, one that's read message 2, and one that has read, again, just 1. And what they are waiting for, that is usually just the next message. But it doesn't necessarily have to be. I think there's some conditions when the thing is about to end, but yeah, basically this is just one more than what you've read. What can happen is that the next plugin hasn't yet requested. So these things, if they're required by another plugin, that plugin hasn't yet been requested to provide its data. So nobody's called next on its iterator yet. So then these things can be equal to each other. So they're either equal or larger than this have read.
Doesn't that assume that the plugin's running in lazy mode?
So yeah, what I'm describing here is the most general case where everybody's running, but the processor is in lazy mode. So you're right that when you're not in lazy mode, then some of these checks are disabled. So I don't think this is being tracked, and this lock doesn't apply. Yeah, that's right. Yeah, so we'll get to exactly what that means in a few slides. But yeah, that's right. So the other thing I show here is a couple of, I show them as locks, but they're implemented as conditions. Technically, a lock is a different programming primitive than a condition. A lock is sort of a thing that's kept globally for each mailbox. Whenever you jump into this mailbox code, the lock is activated. I can show you this in the code. There's here lock. Whenever there's any kind of mailbox modification happening, you always do this with self_lock. And that means that any other thread won't be able to jump into such a piece of code. So that just avoids any race conditions if you place the locks well, so that there's not like one person reading at the same time somebody's writing and everything is going to be messed up. Of course, you can have many threads doing useful computations. It's just when you're placing stuff actually in the mailbox, you're actually getting stuff from the mailbox, then this lock is activated. So those should usually be activated only for a short bit of time. So that's this _lock thing. What I showed with little padlocks over here is rather conditions. So this is something that there are several places where a thread can call wait for a condition. So for example, here in this read method, there is here read condition wait for. So then you give here the condition. The condition is, well, do we have the next message or have we been killed? We'll get to dying mailboxes later. Then we'll wait until this condition becomes true. So the current thread will go to sleep. Then it needs to be woken up by another thread to say the message, hey, buddy, wake up and please check your condition. If the condition is false, well, then I guess I'll go back to sleep. And if it, or I don't know exactly. You shouldn't be waking somebody up if it's if the condition is false, I guess. And if it's true, then you can continue, unless there's this timeout is exceeded. In this case, the timeout is exceeded, you will just end. And I guess the operating system will wake you up and you'll get this timeout exceeded error. But the timeout is by default set to a really large value, so you won't see that in normal operation. So that's what these padlocks are. They're just ways that you can be sleeping, basically. And yeah, I'm going to call them locks, since that's it's an easy way to think of it. It's sort of the thread is locked. The thread is waiting for something else. So in this state, what you see here is that this subscriber, this thread over here, is locked. So it is not running. It is asleep, if you will, because it's waiting for message 3, which is not in the mailbox. The other 2 threads here are open. They're waiting for 2, which is in the mailbox. So you might wonder, hey, why aren't they getting it? Well, maybe they're busy with something else. And maybe they're in the middle of, I don't know, running a neural net or doing something. At some point, they might come back. But yeah, this is the situation now. There's also 2 locks over here, which apply to the sender. So the buffer has room, so that's not a problem. And we can fetch. So that is somebody's actually waiting for the next message that we would fetch. So this number 3, somebody's waiting for that. So we are allowed to fetch. And this is part of the lazy mode. If you're in multiprocessing, we ignore this lock. So even if nobody's waiting for data, we fetch it anyway. And that's useful because then you can read ahead a little bit. And it's not just, I read one chunk from disk and then it goes through all of the plugins and then we read the next chunk from disk. We just read 5 or 10 or however much fit in the buffer, and then things progress. Of course, that takes more memory, but if you're on a, I don't know, 20-core machine, you probably have a bit of memory, and you'd rather have that than have the thing take longer. Okay. So, question for you. What's the next thing that's going to happen in this state?
Well, either the sender is going to try to put something new in, or one of the subscribers is going to finish with what it's doing.
Yeah, exactly.
And then move on.
Yeah, very good. So either we're going to get one extra thing from the sender, or one of the things being received. How do we know which one will happen?
We don't.
Exactly. There's no way to know. So you can, unlike processes, which are really sort of it's an independent process, and it's doing its own thing, has its own variables for everything, and sometimes they're communicating. Threads are not like that at all. A second thread is just like another little worker running through your process and modifying all the same variables. So these workers may be off doing something, and this worker may be off doing something, and who knows which is going to actually come here next. If you're running on a machine with not so many CPUs, then it might be that there's only one CPU, and it's up to the operating system to decide, hey, which of these 3 things is going to get priority. You could try to write an intelligence algorithm for that. We haven't. So it really isn't just up to luck, basically, what's going to happen in this case. The only thing you know won't happen is this guy isn't going to progress because this guy is locked. It's waiting for a message that isn't here. So this guy is not going any further, but any of the other 3 things could happen. So suppose the sender is actually going to put more stuff in. So let's say it puts in another message. So now a couple of things happen. So the sender puts its result over here. That takes up one more space in the buffer, but there's another space left, so it still has room. Now we put in message number 3. So we're going to notify this thread over here that its condition has now been met. So we sort of unlock this thread. Doesn't mean that it starts running immediately, but if you have a lot of CPUs available, then there's quite a good chance that it will start running soon because it was waiting for it. The other thing that happens is, since we placed this message in here, and that is now equal to the maximum of this waiting for table, this lock gets activated. So the sender isn't allowed to put in another message when we're in lazy mode. And that is basically whenever you're not multiprocessing, unless you specifically disable it. So now we know that the sender isn't going to be the next thread to run, but any of these could start to move. So let's suppose it is actually this thread that starts to move messages from the mailbox. So let's see what happens. So it will read message number 3 and update its values here. So now I've read message 3 and I'm waiting for message 4. It won't immediately compute everything possible for that. That is part of what this thread does, but at this stage, all we're doing is just grabbing the message from the mailbox, updating these values, and then as soon as we can, release the lock of the mailbox so that another process can, for example, maybe the sender wants to do something again, and I'll just keep this message, or rather, if you will, a reference to this message. The messages aren't just copied. That would massively increase the memory overhead. It will just keep it in a local variable. Okay, so the thing gets locked again, if you will. It might continue running, but if it finishes running and comes back to this grabbing stuff from mailbox stage, then it will stop and it will wait till the new message appears. The other thing that happens is that whenever a reader gets something, it will look through the mailbox and see, can I clean something? So in this case, I could clean message 0 because everybody has read message 1. So actually, I can also clean message 1. I should have indicated that. I'll correct it before I upload it if I remember. So then it will just clean message 0 and message 1 from the mailbox. This lock is also opened because I am waiting for message 4. So yeah, the sender can fetch again. Okay, so now suppose this process continues. So the sender sends more stuff in, the other threads gets more out, but these threads are, I don't know what they're doing, so something really complicated, and they haven't gotten to this mailbox stage in a while. You can eventually end up in this situation where you have all the messages possible in the mailbox. Then this lock will be activated. The buffer is full. The sender isn't allowed to put anything more in. This thread is locked also because it's waiting for message 6, but there's no way we can put that in because the buffer is full. So this guy is not going to be running for a while. Progress will only be made when one of these threads reaches the point where they start querying the mailbox. So for example, suppose the first one comes, it will immediately read all 5, keep them in some local variable. Remember, it's not copying, so it's just having a reference there. And then it will release the overall mailbox lock so that we can continue doing other things. And this thread will then churn through these 5 messages and do whatever it needs to do with them. It gets locked. If it were to finish those 5, then it can't just progress because it's waiting for 6. Buffer's still full. Nothing can get cleaned because this guy still hasn't read any more messages. Until eventually the final subscriber should get to that. It will also read all the 5 messages, also just keep them in a local variable. Then it will clean the mailbox. So it will delete these things from the global underscore mailbox variable. So then these things still stay alive, right? We still have references to these things here in local variables. So they only get garbage collected by Python once the last reference disappears. Or a little bit later if there's some kind of cyclical reference thing, but let's hope that we don't have that here. It gets locked because it's also read everything. The mailbox is empty, so we unlock this final condition here. And the next thing is that the sender can send in more messages. And that's now for sure the next thing that will happen to this mailbox. Okay, any questions on this?
So just to double check that I got it, this old issue with the max messages being too much, that was basically that the buffer was full of the mailbox.
So if the max messages was too much, you say?
No, there was this, that max messages was too low And then
Yeah.
at some point it would crash if you do something complicated. So you need to turn it up to very high in order for it to work.
Yeah, so that what can happen here, and for that you need more than one mailbox to really get this, is that, for example, suppose this plugin needs to get 3 chunks of this guy in order to produce one output. And this guy maybe only needs 1 to produce next output. So then, yeah, you can get in a situation if you have certain dependencies that, yeah, it will essentially deadlock. I don't have an example right here, but you need some kind of triangle diagram where one plugin is asking for a lot and another is not. So then you need to have a large buffer in order to be able to make progress. So that's actually why this lazy mode was introduced. In lazy mode, let's look at that. So that's ordinary operation. We set the buffer size. Let's see where we do this. Here, if lazy, max messages is infinity. So actually in lazy mode, this lock never gets activated. So you will never get in the situation that the buffer is full. So you will also not see those deadlocks. And you might, if you have a weird enough graph, you might need like 100 things in memory, and that can give other problems. But so usually only one of these locks can activate it, depending on what mode you're running. So if you're multiprocessing, then it can be important to set this max messages high enough. In normal operations, you no longer need to.
Okay, thanks.
Sure. Okay. More questions on this? If not, let me move on to the second bit I wanted to introduce, which is the exception handling. It can also be slightly gnarly. So here we have just a tree of Strax plugins. So you have here maybe raw records at the bottom, and here you have the final generator, which is the object that you see. So that's in dev eater in the processor. Right, so you have this object. So that is the plugin that's where you're actually getting the results out to the user. So it's whatever the user asks for, get the data frame for something. Suppose there's an exception here. So I don't know, somebody divides by 0 or asks for a dictionary key that doesn't exist. So then the exception will be raised here. So what will happen is inside the mailbox where this plugin delivers to, then that will become killed. So when it's looking for the messages that are being sent in, there's a try except loop around it. If you catch an exception, it will set this flag, say, hey, I'm dead, basically. Then when these threads will look for their next message, by the way, if as soon as you're killed, all of these locks open. So we wake everybody up because what we want them to do is to ask for the next message. And as soon as they do, they will receive mailbox killed instead of the normal message. So then they will die. And this guy, which is submitting to another mailbox, maybe these guys are savers and don't submit to another mailbox, will kill its mailbox, open all its logs. All these guys will get mailbox killed as well. So by now, most of the threads are done. They have raised an exception, so they're no longer executing in some loop. This mailbox killed will be called here in the final generator. So here there is a try except. So here accept exception, that will catch the mailbox killed. You see here, hey, if it is a mailbox killed, then let me retrieve what the original exception was. So this value error will be retrieved. The mailbox killed will store that. And that's the one that we will then eventually raise. It could also be that the exception is really in this sort of this last part, and then you won't see that, or maybe you divide it by 0 here or something. So now there's one more problem, and that is this guy. that hasn't been killed yet. So that is especially problematic if this is some kind of multi-processing thing where there's several processes that are producing this, and how are we going to kill all these guys? So what happens is we actually go back from this final generator. It will go through all of the mailboxes and it will kill them with a bit of extra firepower. So it will set this upstream equals true. And that will cause an exception to be raised here. That will actually also here give mailbox killed to whoever is producing this. I am not 100% sure if this state actually needs to be different from this. Maybe we could just kill it in a regular way and that would work. Or rather, we apply whatever force kill is doing, we also apply that whenever the mailbox is killed. But this is the general way exceptions propagate. So they propagate down the chain until you get to the final generator, and that then goes through all the mailboxes once more to check, you dead, you're not dead, then I kill you.
So maybe a naive question, why couldn't you kill straight away upstream?
Let's see, why couldn't I kill straight away upstream? So this mailbox, how does it get the signal if one of its subscribers dies? I mean, a subscriber is just a thread that reads some stuff from this mailbox, and right, so it's just one of, go back to the beginning, right, so you have this thread dies, then it's not that something happens inside this mailbox class, it's just that this thread, which is like a little walker going through the code, has fallen into a hole somewhere. Then yeah, the mailbox does not know. It's just the thread will never get there, but what does the mailbox know about it? I'm not sure how you would do that the mailbox would somehow sense it. The mailbox isn't a thread in itself. It is just a piece of code with some local variables. So let's see. So what does work is if the sender dies. So the mailbox is pulling on the sender. So the mailbox, there's a bit of loop here. Go there. Def sender here. So send from. So there's a bit of code here that does while true. Here next on the iterable. And when this would give an exception, then we can kill. If we are reading. Okay, let's see. So we are reading from, this is one of the things that are passed to iter, right? If you're a plugin, you get these iters argument. So, go back to the mailbox. Yeah, here. Right, so there's at some point a yield. Here, yield result. So you yield the result, great. Now what? Now I'm waiting for another next to come. When there's another next, then I'll continue running the function. But if there never is a next, then I don't get any results. So there is actually an exception statement here, but I'm not sure that would actually be activated unless you throw the exception back into the generators. If you would sort of wrap the iter of the plugin into a try except, and if there's an exception, you throw the exception back into each iterator. That's what I think, but I see there's an exception yield statement here, so maybe there is a way this can get triggered. I don't know.
How is the last mailbox different then? How is the last one able to kill upstream?
Sure. So the last final generator is here. So the final generator, this is part of the threaded mailbox processor class. So that is this thing over here. And it has this self mailboxes dictionary. So it has a reference to every mailbox in the game. So whenever you come here and you receive an exception, right? Because your exceptions propagate upstream, so you will always get it. Then, yeah, you will go through all of the mailboxes and set something in that mailbox. So now I will notify this mailbox, which this thread couldn't do, right? It died. So it can't then get back to, oh wait, before I die, let me tell my mailboxes that I'm about to die. But this guy can inform this mailbox, and then this will, yeah, try to kill this guy with raising an exception.
All right. Yeah.
Okay. So probably there is a way we could do it like that. That, you know, somehow it would also run this in some kind of try except loop, and then maybe, yeah, also raise an exception here. Maybe there was a way to do that. I don't know, but then I'd have to use this .throw mechanism. But
I'm not
this is how we
sure. It's
do it.
like the way I see it. So some thread asks a mailbox for data,
Yeah.
and then it dies. And so the only thing the mailbox is going to see is that this one subscriber isn't asking for data, which can mean one of two things. Either it's, you know, just taking a really long time to go through this data, or it's dead. The mailbox doesn't know. All it knows is that this subscriber hasn't asked for data.
That's right.
Because
Yeah.
the thread actually doing the computation is somewhere else.
Yeah. Yeah, you're right. So that's why it usually does not work. One way around it, which we might have been able to do, is, for example, in this plugin code, what you could do is you have these iterators. And in Python, you can, if you have an iterator, you can throw an exception into it. So you can try except across, for example, the user-defined code, since that's where most likely the exception comes from. No disrespect to the users. Of course, you can have an exception in Strax. Whenever there's an exception, before you raise them, throw the exception to all of my iterators. So then it gets back to the mailbox. It's just like somebody calls next in this point. So I'll continue the execution here, except that I'll trigger this block when somebody throws the exception into it. But yeah, then you would have to modify the plugin code to do that. And that's not how we did it currently. Okay. Any more questions on exception handling? All right, then let me see if I can still exit this full screen. Escape does not work. Anyway, here we're at the code. So then, did you guys have any questions on the mailbox code?
Yeah, so I had one question.
Sure.
I just overlooked it. But in the can fetch method, it says that at least the docstring says that it also can return nuns, but I actually only see trues and false. I actually think that also later downstream, it's actually checked whether there's a none.
Yeah, I see. So returns if we can fetch. If not, it returns none to distinguish from false. But yeah, just returning false. Well, that's not very good.
Or true. Can return.
Yeah,
true.
or true. Yeah, you're right.
I think
yes, the idea.
Yeah, go ahead.
Yeah, so here, if the none would also trigger it. Indeed, the idea is that if a timeout is broken, it would return false. And we want to distinguish between these two cases. But it doesn't look like that's happening.
I think it's used as an argument for some function, and that then later checks if a copy of that argument is also none.
Sorry, you said it's used. So
I think
which
you can wait for.
Yeah, so here, for example, I'm waiting for can fetch. And if this is not true, okay. So what's happening is that this code assumes that if this is false, the only reason that can happen is because the timeout failed. So you must not wake this guy up if the condition isn't met. So before waking this guy up, you need to check the condition again. So let's see, where is this fetch new condition notified? So there is notify all. Exactly. So here we check it again. So that way it works. But yeah, I guess at an earlier point, I thought, maybe I should use returning none instead of false, but I didn't go that way. Instead, I just checked before waking up, but then I didn't update the docstring. So yeah, that's a mistake. Thanks for spotting that. Yeah, I don't really understand why they made conditions work like that in Python, that you have here this condition, and if you call wait on them and the timeout is broken, then you get just false, which is the same result as if the condition isn't true. So I would rather like to distinguish these two cases. They're very different. One means somebody woke me up but shouldn't have woken me up, so then I can get mad at whoever woke me up. The other case is that is a tragic accident and now I have to die because the timeout failed. And yeah, but I don't know. Perhaps there's something else that I'm missing. In general, let me say that if you have some problem in analysis or coding, and your solution is like, let's use the threading module and let's use R logs and conditions and all this stuff, probably that's not the right way to go. There's probably some other package that you can use. And in this case, that package is probably the streams package that Yossi is looking into. But making your own threading code, it's difficult. There's all kinds of race conditions and stuff you need to think about. The mailboxes used to crash all the time. And whenever there was a Strax error, it was like, oh, I see something weird with mailboxes. That still happens occasionally, but it's much rarer now due to this lazy mode, which worked very well, which was actually also developed in conversations with Yossi about how to do this better. Okay, more questions? Maybe any questions on the processor iter code, which was also part of the reading. Very closely connected to the mailboxes, of course. I don't hear anything. So then let's look at the study questions. If my browser will wake up again. That wasn't the intended. Okay, I can still use this. Right. So describe the 3 conditions in which a mailbox can be locked or initiate the waiting period. We've seen them, right? So those are the... Okay, I need to go... Right, so these 2 and this one. So here is buffer having room, this being able to fetch or not in lazy mode, and this is the message that you're waiting for there or not. We also discussed this. A mailbox has only one sender unless it's multiprocessing. It can have more than one subscriber. Generally, it does. How do multi-output plugins fit into this? Did any of you get to that part of the code? What happens in this case?
There's the bit in, I guess it's the processor init, that deals with setting up the mailboxes for multi-output. And it just, for each output of a multi-output plugin, it just adds, it registers senders.
Yeah, so what happens is that for each of the outputs, you will get, let's see what's here. So the main thing that happens is that there is a special mailbox being created. So there is a thing called divide outputs where you will send your result to. And this is the only case where the mailbox, the thing that it receives, is not a Strax chunk or a future yielding a Strax chunk, but a dictionary, because a multi-output plugin returns a dictionary with, for example, here's records and here's loan hits or something. So there's this special code in mailbox.py all the way at the end. Divide outputs, which is the code for running this divide outputs. So it's just given the source and the different mailboxes where the output should go through, and it's just going through. Okay, so for the different outputs that we have, let's get that mailbox. Can we fetch? If so, then fetch a new one. If not, then this is just checking if we can fetch, and if not, then we wait. So we wait until somebody has requested that output. If all the outputs say, yeah, you can fetch, or it's an output where we say, yeah, we're not gonna wait for that output. So there's these flow freely outputs. For example, if you have an output like lone hits or something that isn't requested by another plugin, then it would otherwise just wait forever, since it will never really be requested. So that's why it's ignored here. So if all the outputs are either part of this flow freely or they've been requested by somebody, then we get the next person, or the next result of the multi-output plugin, and we send it to these different mailboxes. So there's a mailbox created at the end of each multi-output plugin. That is this divide outputs mailbox. And then we add readers for all of the different outputs. So I think here we're going through all of the outputs here. Actually, I think we don't create like a reader for everything. It's just that this mailbox, the divide outputs mailbox, has one reader, which is running this divide outputs, which has a reference to all of the mailboxes, and it will just send stuff into those mailboxes. So there are not that many senders and readers. The main thing is that there's just a single sort of mail divider mailbox created at the end. And there's a bit of unfortunate code duplication in here. So there's some stuff that is duplicated. For example, here the exception handling code is a bit duplicated. This was another thing that was added somehow at the end. Multi-output plugins are much younger than mailboxes, and certainly this scan fetch system, that's one of the newest parts in Strax. So that was really hacked on at the end.
You mentioned that, for instance, things like lone hits doesn't get requested by any other plugin. I guess this kind of ties into the next study question. But there are, for instance, the savers that do register themselves as wanting that.
That's
Lone
right.
Hits does have a saver that's registered. A couple lines down. This is around 180-ish.
Yeah, that's right.
So that's still going to be requesting lone hits. Or do savers not quite work that way?
Yeah, so the thing is, there's this can drive variable, and if we set that, then it doesn't count as a real request. So you might wonder, why on earth would we do that? And that's just to prevent one saver from saying, okay, I feel really good today. I'm going to request everything, and I'm just going to keep running, and to however the operating system is running, it's always giving that saver priority. What could happen is that will just keep pulling data. And remember, in lazy mode, we have an infinite buffer size. So it can request the entire run, for example, lone hits, before Peaks has any chance to do something. So a saver is not allowed to drive these considerations. So a saver may want a piece of data, but it just has to wait until another plugin will request it. And then it will also get it, and it can save. But it can't give the signal that, please give me the next chunk. It can't do that, because it can go usually very fast, and there's not much constraining it. There's some exceptions to that again. There's this storage conversion mode, and there's what if you're not in lazy mode, but this is basically how it happens. If you're not in lazy mode, none of this matters. Then everybody always fetches until the buffer is full. Yeah, so that's why this flow freely thing exists. So if there's a data type that's only saved, then we're not going to block for somebody to request that. Just yeah, it's not going to happen. Yeah, so indeed, you mentioned that this ties into the next question. So if you have an output that's not requested by any other plugins, the mailbox can still be emptied, right? So since there is a saver, right? So that will still request the things. It just won't set this this can fetch mechanism. So what happens if lone hits are not saved? What happens to this lone hits mailbox?
There'd be nothing that's actually, there'd be no registered subscribers to that mailbox.
Mm-hmm.
And then you'd get a value error when you try to start.
Yeah, so there's a mechanism for that. You're right. So we have here in iter, starting threads, and then I guess in start here, yeah, if there's no subscribers, you'll just get a value error. That's right. So I saw that value error at some point, and then I thought, oh, that's not so great. I mean, I want to process anyway, even though nobody requests lone hits. So what are some ways, what are ways that we could deal with that? And then we could talk about which way I eventually chose.
I guess one option would be you have some kind of dummy plugin that asks for this data in, sort of kind of like a saver and then just dumps it.
Yeah, exactly. And that's exactly the option I chose. So if you look here, you'll see at some point, see where it is. Here. So we figure out which output we should discard because they're produced, but they're not required by any plugin and they're not saved. So that we get over here to discard. And then at some point here, here's my little dummy plugin. So can't get much simpler than this. We just iterate over it and then do nothing. And we just add that as a reader. So it needs, yeah, that's what happens. I guess the only other option would have been somehow not make that mailbox. Not really sure how that would work. Then you'd have to tell the other plugins like, oh yeah, don't submit that. That output's not wanted. Keep a list of the unwanted outputs and discard them there. That's fine too. Here we just did it like this.
So then the check in mailboxes never fails basically because processor will see that nothing has registered this, and so it will register a discarder.
Exactly. So this is just a sanity check that will prevent this situation from ever occurring and causing more problems. For what would happen if I actually were to start a mailbox with no subscribers? What do you think would be the result if somebody were to write in it?
If you're in lazy mode, you crash because you run out of memory because the mailbox is full.
Yeah, indeed. So that so if you're in lazy mode, then nothing is requesting this mailbox. So I guess you wouldn't be able to write in it. And then so that would produce a timeout error at some point. Somebody tries to write in it, but you can't because it's locked. Nobody's requesting it. But if you're multiprocessing, you're right, and it will just fill the entire buffer. And that is finite in multiprocessing mode. So you can only put like 5 things in it, and you will again see a timeout error. Either of those are not incredibly informative, and those timeouts are set to a long time for a reason, because if those are triggered, yeah, I don't want them to be triggered ever. That's just a kind of a fallback. And the reason those timeouts are set to long values, and we talked about this already, that if you set them to 1 minute and some plugin actually takes a minute to process a chunk, then the timeout fires and you die. So you want to set them to very long values so you don't have to worry about dying from the timeout. But you want to have something there so that it's not just that some event builder hangs forever and you just never know. It just consumes power. Yeah, so that's why this check is here, just to prevent that odd situation from happening. but it should never trigger. Okay, then exception handling I also covered. So I covered the steps leading up to this. Yeah, so if you're at this stage, all of the threads have stopped executing, and it's just a matter of doing some cleanup. So that you will find in the processor.py, in the iter here. So I've gone through this step. So right, let's start here. So you get a final generator. You get some exception out of this guy, right? That's what's coming out of the end. That will usually be mailbox killed unless the exception happened really at the last part. So you get the exception here, you get the original reason back out. You don't have to worry about this. Then we get here, we kill all the other mailboxes. And this is really just, I set some flags, so it's not gonna, right, look here, to kill. Okay, so I have to request the lock. So I suppose it could hang because somebody's hogging the lock or something, but I think that should be pretty rare because the lock is released as soon as we can. And then we just, we set some flags and notify people, and that's it. And so then we have to wait for the threads to realize that they have died. That's what happens here. That's cleanup. So here in cleanup, we go to the threads and we do this method called join, which will wait for the threads to die. That should happen relatively quickly because we've sent this message, but I think Johan had a situation where actually they didn't die. And that's unfortunate because then you will exceed this timeout, and then I don't know what to do. I can raise an exception here, but another thread is still running, so Strax isn't going to shut down. So this is a bad situation. In this case, probably we have to kill the entire process with some brutal method, send some sick kill to yourself or whatever to make sure that you die.
Or stop rsync, that also helped.
You said stop rsync, that helped?
Yeah, no, I was just joking. But
okay.
The reason that we reached this timeout was actually that one of the savers of raw records was never finishing because I think it was a combination of circumstances because both the disk was really full, which already really slows performance, and rsync was performing. It was like requesting many raw records all at the same time. So it was just never able to write anything to disk. And as this is the lowest thing, then that's probably why it ended up in here.
Yeah, that makes sense. We usually start like 7 or 8 rsyncs at the same time, or rather there's one process that starts these things. If they're all requesting raw records from one event builder, then that can be a lot of disk load.
While we're getting sidetracked on this, I'd imagine that the disk bandwidth is probably better than the network bandwidth.
Yeah, maybe.
I mean, network bandwidth. Your best case, 10 gigabits. I'm pretty sure you can go much further above that, writing to a disk that you're physically connected to.
For a hard drive, I thought was the read rates like a couple hundred megabytes per second is that's pretty good. So if you've got a 10 gigabit network connection,
maybe.
Yeah, SSD, you're definitely right. Sure, you can. Will be a while before you max that out. Okay, maybe just to finish the cleanup sequence. So in a normal situation, the threads will die here. Or you also do this when just the processing is finished normally. Maybe I should mention that in that case, the message that's being passed here, instead of a Strax chunk, you will see the thing stop iteration, which will cause this to the whole process to end normally. So then we still need to shut down the executor. So if you activated multiprocessing or passed without multiprocessing, but you did pass like max workers equals 15 or whatever, there'll be a little pool of threads that you can send work off to, and we need to make sure those are shut down. They shouldn't have any work left at this stage, so that the wait shouldn't be triggered unless maybe some kind of process is stuck, and then this could again hang forever. That would be bad, but I hope that doesn't happen. Chris, you had a question.
Yeah, I was wondering when would be good for a more general question. I don't know if now is a good time to. It's.
Yeah, I think So let me just finish these last few lines, and then will that be okay?
Yeah, perfect.
Okay, so we're almost at the end of the cleanup. So if there is an exception, we will now raise it here, and then the final thing which we do is, if there's a saver that, like in this final last thing has another exception, but the mailbox is already closed, then that triggers a crash, but that doesn't it doesn't get registered anymore. So that we go through all of the savers and just check, hey, did you get an exception? Make sure that's at least raised, so that it's not like Strax shuts down normally, but when you look at your data, you see, oh, there's an exception. So then you see processing finished, and then it's done. And you get the array back, or your data frame. So yeah, that's all there is to it for mailboxes and exceptions and everything. So, any questions, general or otherwise?
If you don't mind me starting with a more general one.
Go ahead, Chris.
I'm trying to skip another talk that's running. Sorry, it's in the background.
Of course.
So I get why we have mailboxes. I thought this was a nice overview. What I was wondering was what you thought the pros and cons of this approach were. So I don't think we're going to. I don't think we have to change how we do the mailboxes, even though Yossi's ideas are sort of interesting. Mm-hmm. But I guess I'm trying to figure out what you consider the strengths and weaknesses here, and if you see any big projects happening with regard to mailboxes for some deficiency, like in the long term. If you see what I'm getting at, just sure. Like a bigger idea of where things are at, because this is really like the pits of Strax, and also there's a lot of like very custom code for things that we like years ago thought, okay, maybe it could have been one way or another, like using some other, exactly. Where we closed and we reopened, but like was this the right way to go? I'm guessing so, but
well, in one sense it is, because it works most of the time, and
for now.
So for now, exactly. So in that sense, it worked. I learned a lot while making it, so I guess that was also good. And maybe I wasted a bit of time, that was less good. But yeah, we went back and forth on this. And so first our idea was, let's refactor this into another package and make it really nice for other people. And then at some point realized, well, it's turned into this really complicated threading code with lots of special cases. And then I started some other piece of work, some kind of scheduler. I don't know. I have a link somewhere, but that never worked either. So then, that's this other piece of work. And then Jossi came in and said, "Hey, this it worked. Maybe I can look at it and make it nicer." So then Jossi did some research on all the different kinds of frameworks. I did a much less thorough research when I started work on this, just looking at the different things. Many of them didn't exist, or were much less cool at the time. So one disadvantage of many of these big frameworks is that you have to adopt this big framework, right? You have to maybe install some kind of Java engine that does the streaming, but there are also packages that are relatively more compact. So you'll see look through some of them, and we really can't do his research justice at the moment, but he went in quite deep. So more people got involved. So now I chimed in at one point again, said, hey, this is what they generally do. But here's basically the problems. The big problem I see is that there's no scheduling or prioritization. So when you get to a situation like we had at the start of the talk, like this, what's happening next? And that depends completely on the operating system. So it might very well be, certainly if we didn't have lazy mode, that you just, one sender sends in a lot of stuff and nobody requests it. So a better prioritization would be great to have, and that could lead to lower memory footprint and lower, just faster speed. This has been addressed. The deadlocks, we don't have that anymore in lazy mode, and the exception handling is just a nightmare of a code. But one of the main advantages, which was that it wasn't so much code, it was like a few hundred lines, and the person who wrote those lines was part of the team. That's going to disappear. So yeah, I hope that we can replace this with something that is relatively thin, but has a better scheduling and just has much less lines in Strax. And I hope that's what Josty's approach will do.
Yeah, that'd be great. I think that since the DAQ is driving a lot of the, at least initial design for the mailboxes, the situations, well, at least I'm thinking about it, but it sounds like Yossi's thinking about it too, is if you wanted to somehow have like hundreds of just more or less a cluster of plugins that behind the scenes, which might make analysis a bit more straightforward, especially if we start going more Jupyter Hub type approach. And then there's the other side of, which is another thing I'm thinking of, if we integrate a lot of like GPUs into somewhere and try to come up with more complicated architectures where maybe things need to block more than others, or you might be fiddling around with this for that. I mean, if you're talking about like tens of, I don't know, either like a handful at LNGS or tens of them somewhere else.
Yeah, these are all things you could build on top of this, but not really on this mailbox thing. You don't want to build some kind of fancy GPU support into this custom threading code. You want to use like Dask or something like this, I would guess.
I didn't mean because they were GPUs, but just since you might be having one that is just like significantly slower than the others, you might, that might mean you hit some, I remember there being like timeouts and things like that we would hit earlier on when there was a super slow plugin.
Yeah, that's still the case in multiprocessing, that you have some timeouts. Yeah.
So do you see this as a big thing that has to be done at some point in the lifetime of Enton? Like really try refactoring a lot of this mailbox stuff, or will it just go the PAX route where it's sort of like just dies lonely and, and unloved? Or it really depends on how things go. I don't know if you had big things on your horizon or on your, I don't know, list of things to do.
I mean, if you wanted to make a list of what are the most critical issues in Strax to solve, I wouldn't put this at the top, because for most purposes this works fine. There are some tests of it, but yeah, there are possible issues that if you hit an issue, it can be quite gnarly to find out what the issue is. There's no way you can go to Stack Overflow and just ask some expert, because we're the only ones using this. If I were to say what are the more critical issues, I think there's basically two. One is this one. So if you have a time range selection, you get this weird error sometimes if you have an object at the edge of your time range selection. And I think, Chris, you and Yin Fan hit this a few times when you're waveform watching. You can, if you choose a time range that isn't nice, you get this error. So yeah, that's going to be a nasty issue. Well, I hope it's quick to fix, but I don't know how to fix it. So, and then the other one is, let's see, which one is it? Okay, so there are a few issues here and here which have to do with exception handling in mailboxes, but they're pretty rare. Let's see where the other one is. This one, I think. Okay, no, this defaults in runlock, but in general, the initialization of a Strax environment, of a Straxon context, can be very slow, especially this data availability check, because for every run, we are currently building this entire computation graph of plugins to find out what the hash is. If you do this for 10,000 runs, then you're going to be there a while. So this process will, in a few months already, become very slow, and in a year, you'll start the context and We'll just be waiting forever for the availability check to complete. So that's an important feature, and it would be great if we can make this faster, either by caching the hashes somewhere or making the hashes no longer run dependent.
Or could
So
we?
those are the two. Go ahead, John.
Couldn't we just give a? I mean, we're not interested in runs 0 to 1,000. Couldn't we just add some argument? Okay, just look for these kind of runs.
Yeah, we have that already, in fact.
Okay.
So-
Thanks for the overview. I have to actually run to something else. So thanks.
Sure, no problem. So we have that here.
Yeah, there is, first real run starts at 7,000, in this case, 7,157.
Yeah, I'm just
But,
saying.
I mean, so right now, because we
I
have
can't find
8,500 runs,
Mhm.
cutting the first, 7,157 does cut down quite a bit on the amount of data we're sifting through. But fast forward a year, we've just picked up 10,000 new runs. Fast forward 2 years, 3 years, now, 40 or 50,000 runs in the database. Dropping the first 7,000 is a rounding error.
Yeah. Yeah, and it's not just the availability check. It's also when you're actually loading 10,000 runs, which will at some point happen. So then you don't want there to be some like order second overhead for loading a run. I don't think it's that bad, but there is some overhead for loading each run. So that's super runs would be a solution to that, but still, this is one place where Strax, in terms of performance, is at the moment worse than PAX, because PAX didn't have to do the whole computation graph stuff. It just loaded some file, or hacks in this case. PAX didn't do any multi-run stuff. So yeah, that issue with the hash differing per run and that requiring an entire computation graph, I think we discussed this either last time or time before that. That's a big one, together with the time range thing. Those are the two things that I would put at the top of the list. And then the Mailbox refactor, yeah, it's great, especially what Jossi showed us last time with all the profiling and nice viewing. That would be a great improvement. But if it never happens, I think the experiment will still run without too many problems. Though I think once we have it, we will never want to go back to the whole Mailbox thing because there's so many other nice features. So other questions, general or otherwise?
I'm not sure how much this counts as a question, more of just sort of wishful thinking. So I've worked at a small amount on something that's similar to the Mailbox system that I was going to, at some point, plug into the readout software. Because currently we have n number of threads that are responsible for reformatting the data from the digitizer format into the Strax format, and then it compresses it as well. And in principle, you could separate these two tasks very, very efficiently.
Sure.
And something a nice feature I had wanted to add to this would be dynamic thread scaling. So the number of files that we write to disk needs to be fixed because that's how we communicate run progress. But the number of threads that we're basically doing data formatting, if there's a very low amount of data coming through, you can get by with maybe 4 threads or something. But if a PMT flashes, all of a sudden your buffer fills up and the software says, all of a sudden I have 10,000 things that need converting, and it spools up more threads. In principle, so looking at how the Mailbox system is currently built right now into Strax, this doesn't look like it would be even remotely possible because you'd have to make new plugins and then, or like instance new plugins and then dynamically subscribe and then dynamically unsubscribe. So do we think this sort of kind of feature would even be remotely worth thinking about? It would help for, if there are slow running plugins and the OS or the software would assign, more power to these plugins to keep moving data through them. So if it takes 20 seconds to process one chunk, and chunks of 5 seconds, then sort of steady state, you'd end up at 4 threads running on that plugin because, well, then you kind of keep up with live.
I think the approach we took here for Strax is just to have this large pool of worker threads. So you have this thread pool executor that contains maybe 20 workers, and they just get assigned whatever task is necessary. So if that's raw records computing, it'll do that. If it's peaks, it'll do that. The only and there's a similar mechanism for processes, for plugins that work per process. You were talking about what if threads were more closely associated with a piece of work, how to then dynamically scale that. For example, what if it wasn't in the user-defined work that things take a long time, but it is rather the overhead in the mailbox, for example, where things are concatenated or something like that. Yeah, then I'm not sure how you would have multiple threads working on that. But okay, if you're thinking of making or using a generic sort of stream computing scheme with dynamic assignments, I definitely look into the work that Jossi is doing and the research that he did to see if you can use any of those systems for your purpose.
Yeah, I see Yossi scarpered. Otherwise, I would have asked if this kind of scheduling kind of falls under the stuff that he's working on.
Mm-hmm. Okay. Any more questions? Mailbox related or not?
Maybe a naive question to Daryl, but couldn't you just do that with giving the threads a different priority level, like a different niceness level?
Probably.
I think you can do that with an OS command.
True. Messing around with dynamically adjusting niceness from inside a process seems like it's got potential to bring everlasting pain.
Yeah, I guess it's like sending signals to yourself or something. It can be done. I don't know.
Because I'm not sure that. So like I guess there's two ways you could look at this. You can ask the operating system to give priority to certain internal threads. I guess so that would be if you have the same as or perhaps slightly more threads than you have cores available to process. So everything is, some threads always have to be waiting. Then you could ask the operating system to prioritize these threads over others. But I think, so if you run in a system where you have essentially some overhead in terms of the amount of CPU you can use, I'm not sure if having the operating system do that scheduling would help. So if you have one plugin that's running long, if it takes a long time to process a given chunk, it doesn't really change much if you ask the operating system to schedule this thread with higher priority, because it just runs really slowly. You want to, I guess, allocate more threads to that specific task, because the number of threads currently allocated is insufficient. Maybe, I'm not sure. Task allocation and at the operating system level is probably beyond the scope of this course.
Pretty sure, yeah. So any more questions on mailboxes or other things?
So I'm still busy formulating the end of this question. So we've noticed with Bootstrax that as the data rate goes higher, we have to run with fewer messages because each specific message is going to grow in size considerably. Mm-hmm. It seems like there should be a way where you could, so rather than Joran sits down with a notebook and uninterrupted access to Ceph and that event builder for a certain amount of time. It seems like there should be a way to figure out exactly what values you can use based on a rough understanding of how much overhead there is and how large each chunk would be. Especially, so with Python, I'm very often never sure if you get a reference to something or if you get a copy of that something. And especially when you're dealing with chunks, if your chunk is a couple of kilobytes, it doesn't matter really if you get a reference or a copy. But if you're loading, a chunk of say the most recent raw records, which might be, 2 or 3 gigs, it makes a very big difference if you're getting a reference to the copy that's in the mailbox or if you get a copy of the one.
So in Python, usually you get, it's sometimes described as an intermediate between pass by reference and pass by value, which is not really helpful. But you're always dealing with sort of references to a sort of lower level where the objects reside in memory. So you can sometimes make copies explicitly, but usually you always have a kind of references. But okay, to get to your main question is, can we more intelligently choose this max messages requirement? Yeah, I hope so, but I'm not really sure. So, I mean, the danger here is that having a too large internal buffer means, you run out of memory, and now I hope that would be a gentle error at some point, but it isn't. You will just get some weird error, I believe. If you have too small, you will get these deadlocks, and in general, it might go a bit slower, as I think Johan found out in the benchmarks. So one improvement you could do is having this lock here, or whether the buffer has room, not be controlled by the amount.
Screen at the moment. Sorry, Jelle.
Thank you, Johan. I've completely forgot. Let me reshare the screen. So if you have this lock here, whether the buffer has room, let that not be decided by the amount of messages that are in the mailbox, but by the amount of memory that these messages take. You could also look at maybe trying to optimize what's happening when a thread is reading many messages. So when we went from here to here, a thread is suddenly reading 4 or 5 messages and then keeping a local reference to that. So in this case, you can end up in the situation, for example, after this has happened, that the mailbox now has 5 slots available, but there are also still 5 messages where there are references here in these local buffers, so they still won't get cleared. So you can actually get twice as many things loaded. So you could try to optimize this. That will of course have another penalty, like if you require a thread to first have processed one and then get back to the mailbox, then you might end up waiting on mailbox stuff a bit more. But that's something you can do. I guess these are 2 things that you could do without changing the whole system.
So how about this? Couldn't we change the amount of mailboxes just based on querying how much percentage of the RAM is being used at the moment? And just say, okay, well, if there's more than 90% of RAM already being used, then just block it, especially in multiprocessing mode. Yeah, you could do that. So you have this buffer, this lock, you mean, or this condition decided by the total amount of memory used. Yeah. So like the amount available versus the amount that's already being used. Yeah, so that could work, except that if you can never lock all of the mailboxes at once, because then you can't progress, then you can't deliver the results. So you need to know which mailbox to lock. So
yeah, you then need to be a bit careful about how that works, and I'm not exactly sure how you would do that. You need some kind of prioritization mechanism.
Yeah, or you would just limit new mailbox from being released at that moment.
You limit new mailboxes from being released.
As in that there are new mailboxes being activated at the moment. For instance, if you go a little bit down this presentation where you say, okay, now there's mailbox 1 is free. You say, well, we don't want to. Well, not so much down. A little bit. Een beetje terug.
Okay, here?
No, I think 2 or 3
Oh,
slides.
here. Yeah.
Yeah, there. So here you
Yes,
say,
so,
okay, now we can start mailbox 0. But before you do that, you check, is there also enough memory for me to start mailbox 0?
yeah, I see what you mean. So just in terms of terminology, this whole thing is called a mailbox, and these things are just, slots, if you will. But okay, I see your point. Yeah, that you will say, hey, there's still work to do here, right? There's threads that haven't read these messages. So maybe I should use, for example, this can fetch mechanism or this to do some kind of hybrid between lazy mode and multiprocessing, right? In lazy mode, I'm not going to request message 4 in this case because nobody is, okay, I will actually request message 4 because this guy is waiting for it. Or, well, that depends on whether these guys are freely flowing or not. If they're not freely flowing, I won't request message 4 because I want everybody to request it before getting it. So yeah, you could try something like that. So lazy mode in effect does this, and you could have some kind of partial lazy mode or something like this. Yeah, you could play with those things. Okay, any more questions?
Maybe not a final question, but a comment. We can spend a lot of time talking about things that would be nice to add into the mailbox system, but multiprocessing, like this level of multiprocessing and memory buffering is, shall we say, fun to work with. And I wouldn't actually suggest that we try to implement any of these suggestions because that way lies madness.
Yeah, you can get stuck on this. That's right. We also have an experiment to run and data to analyze. Yeah, that's a good point. Yeah, so I think for whoever is left in this chat, you can be proud of yourself. You went through the entire journey from tutorial to the deepest problems with the deepest parts of Strax. You will have seen essentially everything, and the few parts we didn't cover are perhaps not so very interesting, like how NumPy data types are parsed into lists or the other way around, and you can easily get that. So you now know all of that, and I hope this won't be the last meeting where we discuss or you discuss Strax development. There are still issues to deal with, if not in Strax. I think there are some issues in Strax, at least in Straxen. So I hope that the next step will be that a few of you will volunteer to act as the first maintainers for Strax and for Straxen, together with the analysis coordinators. As you know, I will be moving on to another job starting sometime in August, or officially starting in September. If you hit some very serious problem, you should now be equipped to handle it. But if somehow there's still an issue, you know how to contact me. And I think this was it. And I wish you the best of luck. And I hope you won't have to descend in these deep layers to solve the analysis problems. But if you do, you now have the skills to do so. So thanks everybody. And that's the end of Straxferno.
Jelle, thank you very much.
Thank you.
No problem. Talk to you guys some other time.
Thanks a lot, Jelle, for all the useful courses.
Sure. Bye.